In this module, I'm going to introduce you to the idea of vectors. As a fundamental idea, we have to distinguish between a vector and a scalar. A vector is going to be a quantity that has magnitude and a spatial direction, while scalars are going to have a magnitude but no spatial direction. Before we get too far in our discussion of vectors, we need to discuss some preliminaries, namely the frame of reference. Our frame of reference is going to have both an origin as well as directions associated with it. The origin is going to be the place where our frame of reference starts. From the origin, we are going to draw a straight line, which is going to represent an orientation. That orientation usually represents a spatial dimension, so we're going to label it appropriately. Next, we need to talk about the idea of sense. If we have an orientation and we put 2 points on that orientation, going from A to B is going to be one sense, and then going from B to A is going to be the opposite sense. If we put those two things together, the orientation and the sense, we get a spatial direction. As I mentioned previously, usually that line is going to represent a spatial dimension. We draw 2 lines, each going infinitely far from our origin. Going from left to right in this case is going to represent the positive x direction, while going from right to left is going to represent the negative direction. Now, if we're talking about going in 2 directions in 2 dimensions, conceptually it's no different. We're going to start with an origin. We're going to have an orientation which will extend infinitely far in both directions, which represents a spatial dimension. We label one direction the positive direction and the other direction the negative direction. Now, if we're going to add a second dimension to that, again, that will represent another spatial dimension that we will extend infinitely far in both directions, and we will label one as being the positive direction and then the opposite direction as being the negative direction. For a frame of reference, though, this starts to get fairly cluttered. So normally we're going to go ahead and we're going to move the annotations for the negative direction because they will be understood from the positive directions. 3 dimensions get very, very tough to interpret just because the graphs are really hard to read. So in that case, it's usually easier to break our 3-dimensional graph up into 2 2-dimensional graphs in order to get a better depiction about what's happening. Now for angular motion, again, we are going to label our positive x and our positive y directions, each representing a particular dimension. Now our third spatial dimension is actually going to be perpendicular to the 2, which in this case here comes out of the screen. That's usually going to be understood, and we're going to go ahead then and remove it, and usually we will talk about as a frame of reference having one axis that's going to be our reference axis, and then everything else is depicted relative to that reference axis. Just like we had positive and negative directions associated with linear vectors, we are going to have positive and negative directions associated with angular vectors. Any angular vector that goes in a counterclockwise direction is usually represented as being in the positive direction, while any angular vector that goes in the clockwise direction represents the negative direction. Now, as you may have already surmised, vectors are depicted with arrows. The arrow is going to point in a spatial direction. So in this case here, we have a vector that is pointing up and to the right, and in this case here, we have a vector that's pointing down. The length of the arrow indicates its magnitude. A short arrow represents a small magnitude, while a long arrow represents a large magnitude. We depict linear quantities with straight arrows, and then we depict angular quantities with curved arrows. Now that we understand how vectors are represented, let's talk about how we can manipulate those vectors. First, let's multiply a vector by a scalar. Let's say we have a vector and we want to multiply that vector by 2. Well, we're going to take that vector and we are simply going to double it. We are going to put the tail of one vector up against the tip of the first, and then we'll just draw a line from the tail of the first vector to the tip of the second. Let's say we want to divide a vector by a scalar. Well, remember that if we divide something by 2, it's the same as multiplying that thing by 1/2. So we'll take our vector, we're going to multiply it by 1/2, which means that we're going to take our vector, we're going to chop it into 2, and then we will remove 1. Let's say we want to multiply a vector by a negative scalar. In this case, we're going to multiply it by a -1. We're going to take that vector. When we multiply it by -1, we take the vector and we simply orient it in the opposite direction. Now let's look at how we would add vectors together. If we have a vector and we want to add a second vector to that, what we're going to do is we are going to take the tail of the second vector and put it against the tip of the first. Then we are going to draw a third vector, which is going to go from the tail of the first vector to the tip of the second. That vector, in this case the red one, represents the addition of those two vectors together. Conceptually, we are going to do the same thing when we add angular vectors together. Let's say that I have one vector here, and I want to add a second vector to it. Well, I'm going to put the tip of the one vector up against the tail of the second. And then I will draw a vector that goes from the tail of the second vector to the tip of the first. In order to subtract vectors, say I have one vector and I want to subtract another, the first thing I need to do is take my second vector and multiply it by a -1. Then I will add the two vectors together like I did previously. Next, let's talk about taking a vector and breaking it up into its components. Let's say I have a vector that's not going along any one particular spatial dimension, but somewhere in between the two. What I can do is I can take that vector and I can break it up into two vectors, each vector going along one of the particular dimensions. I can also move it so that the tip of one attaches to the tail of the other, or I can put the two tips together. All ways are representing the same scenario. If I take another scenario, again, I have a vector that's not going along one particular spatial dimension, but somewhere in between the two. I will draw lines that will indicate my two spatial dimensions, and I will draw vectors that are along each of those particular dimensions. And again, I can put the tip of one to the tail of the other, or I can put the two tips together, and they all represent the same scenario. Now, obviously, if I have a vector that's going along a particular dimension, whether that be one dimension or the other, then I don't have to break it up into its components because it is entirely along one of those particular dimensions. And there you have it. That's our introduction to vectors.